Okay. Okay. So I don't have the possibility of rewatching the previous video, so you have to tell me where was the point where the connection stopped. No. No data. Okay. From which point should I restart? From which point should I restart? Oh God! Okay, like the last point, the connection was broken, I guess, at the box plus. 26. So we were after the correction of the box plus. Okay. Did I talk, guys? I mean, I don't have the possibility of accessing the video. I will try now, but I don't know where. So I will have to stop the streaming, and this is quite tricky. What I would like to know is that did I start to talk about the landmark, the total least squares landmarks? try to see something in studio. Oh. Video. Now, 1 hour 17 minutes. Okay. Oh, I'm watching myself on YouTube. Okay. Well, it's terrible. Excellent. Okay. Very good. Actually, like, yes, I just fixed that bug, the bug of the excessive parameter calls, because I can't stand it. And also, it's a recommendation for you that when you do a program, you don't put non-necessary parameters in the functions, because if you do so, you create inconsistent. Because, for instance, in this case, if I would have put a number of landmarks which was wrong, while it could be perfectly desumed by the dimension of this matrix, then I could have messed up the things. And maybe in one part I was using the dimension of XR, in the other part I was using the argument that I was passing in, and then everything was crashing. So, program in a defensive manner. Okay? It was not a bug, it was a horrendous style. Okay? Probably written by myself, but that was the game. Now, what is this system is doing is straightforwardly assembling the quadratic form, which is H and B, calling the individual classes of measurements. This will construct the contribution of 4 H and B stemming from the landmark measurements. This will construct the contribution, which is additive. The contribution for the projections, and this will construct the contribution for the poses. Observe that all these contributions are additive. Okay? They are additive, and the mechanism works because all these linear systems agreed on the structure of the matrix H. So they know what each block means. Okay? At the end of this soup, at the end of the linear system, the construction of the linear system, we calculate the global perturbation, we apply to the next state, and we are done. What we will be doing now is to have a look at the contributions to construct this linear system for the different classes of measurements. Let's start about the landmarks. I recall that the arguments of this function are the robot position, the landmark position, the measurements, the associations, and potentially a kernel threshold. And the output are H and B, the total key and the total number of inliers measured according to the kernel threshold. Okay. As always, we will have a function that will accompany us forever, which is landmark error and the Jacobian. This is the landmark error and Jacobian of multi-point multi-pose registration, with one substantial difference, which is that in this particular case, the robot position is not the position of the word with respect to the robot, but it's the position of the robot with respect to the word. And you can see here that I take the robot position and I invert the rotation matrix by calculating its transpose, and I invert the translation vector by calculating minus R transpose times T. Okay, and then the Jacobian is slightly different, but the message is the core is exactly the same as in the other exercise. Okay, if you want to do it by hand, you will figure out that it's not so difficult to compute. Okay, clearly I will have two blocks in the Jacobian, do two contributions. This contribution will be 3 by 6, and this contribution will be 3 by 3. This is the robot landmark, and this is the landmark contribution. Okay, and this will nicely calculate the thing, not caring about the indices nor the structure of H. Is some function that I take, copy and paste when needed. Okay, I wonder why I was kicked out but it seems that Google is having some malfunction. Now we will talk about the assembly of the linear system, and we think about designing the function. What do I need? I need to know the robot position, the landmark positions, the landmark measurements, the associations, the kernel threshold. I need to construct the dimension of H and B accordingly, and this I can determine by looking at the dimension of these objects. The system size will be equal to the number of poses times the size of a pose, so 6 times the number of poses, plus the number of landmarks times the dimension of a landmark, so 3 in this case. We resize and 0 H and B, and then for each measurement we have to go based on the associations. We have to go to the state and pick up the right components, which are the components that appear into the association vector. So we have to pick up the pose index, so it's 1, 2, 3, the number of pose, and the landmark index. We pick up the measurement from the measurement vector for each measurement, right? We pick up the landmark, so this loop is repeated for every measurement. We pick up the landmark according to the chosen index. We pick up the robot position according to the chosen index. These two elements I repeat are in the association vector that has to have the same size of the measurement. Then the first thing that we do is calculate the error and the Jacobian. If the error is too big, we kernel it out and we say that it's an outlier. Otherwise, we say that it's an inlier. Fine. We calculate the key as the contribution of the total key, and then we have to copy the blocks to add the additive contribution to the global H matrix by retrieving the indices into the indices in the matrix that correspond, and in the B vector that corresponds to the landmark and the robot position under investigation. And this is the contribution. Remember, observe that here we have a plus equal in the 4 blocks of my j omega j contribution, and these are the contribution in the B vector. Okay, we have already seen this in the pose landmark problem. Okay, very good. Then we proceed, and this will presumably assemble in the same system matrix the contribution of the pose landmark constraints. Then we will have the same for the Then we will have the same for the projections. For the projections, we have to do basically the same thing that we have done for the landmarks, with the difference that this time a projection might potentially not appear inside the current camera frustum. So might be outside the image or might be behind, in which case we might simply say that the point is invalid and we disregard the corresponding measurement, which means that we don't touch H and we don't touch B. Okay? To do so, we define a fantastic function which we call projection error in Jacobian that calculates the point in the reference frame of the camera by simply multiplying, calculating the inverse of the robot position, ER and ET, same as what we have done for the robot landmark case. If the point is behind the camera, we say no, is valid is equal to false, so we know that it's false. And then we start calculating the contribution of the Jacobian, that it also in this case will be 4. I invite you to do the calculations by hand. An additional thing that we might want to do is to figure out whether the measurement falls outside of the frustum. And in case it falls outside of the frustum, we exit with this valid to false. If everything goes well, we return to Jacobians, JR and JL, where JR will be 2 by 6 and JL will be 2 by 3. Okay? The assembly of the linear system works exactly in the same way as in the case of the post-landmark problem. Curiously, also the size of the blocks of the H matrix are the same, because the size of the blocks involve only the state variables. The values will be different, but consider that here you have a 2 by 3 matrix, and here you have 2 by 6 and 2 by 3. Okay, consider that. Now, when I compute the contribution, the robot-robot contribution will be a 2 by 3 transposed, so 2 by 6 transposed, so 6 by 2 times 2 by 6, which makes a 6 by 6. The post-landmark will be 6 by 3, because you have the 2 by 6 which is transposed, and you have the 3 by the 2 by 3 which is non-transposed, and the other blocks will be 3 by 3 and 6 3 by 6. Okay, this will be the contribution in the H matrix, which is given by the projection contribution. So this is bundle adjustment basically. For the poses, not much changes. Only that we have a little bit more complicated Jacobian that was explanation you find in the slides. The Jacobian will be in this case 12 by 6. So, and one will be the opposite of the other. And this is visible here because we are using the chordal function. And the building of the linear system mimics in total the other part. Clearly, the post-matrix index and the post-landmark index, so the indices inside the matrix, will be different in this case. Okay? And I've done my program, right? I think I unveiled every aspect. Now, by enabling or disabling some of these build the linear system poses, build the linear system landmarks, and so on and so forth, I can have fun and I can compose the different aspects of this machinery. And let's see how it works. Would we like to have a problem with landmarks, no projections, and odometry? Okay, no landmarks. Okay, so this is to suppress. So in case we have we uncomment this line, we are clearing a measurement vector, and so the class of measurements will not be considered. Okay, and let's see what happens. I invite you to run the program together with me, and this is the outcome. It's quite interesting. So what we see many things in this plot. What we see is the structure of the Jacobian, okay? The structure of the H matrix. This is the pose constraints. So this is the pose part, I can imagine. This is the landmark part. And this one here is the robot landmark part. So if this robot observes a landmark, this landmark over here, then here I will have a dirty block. Okay? And that's the essence of the thing. Funnily, if I zoom in, you see these tiny little blocks here? These tiny little blocks are a one that I put in the system, which is called dumping, is an identity matrix that I add to the H matrix in case the system is poorly conditioned, which might occur in case I do not observe a landmark. Just to highlight this, I could simply rerun total list pairs by setting the dumping to 0. Maybe. Did it work? Yes. Here you see that I don't have any more that odd structure that I was observing before. Okay? Unfortunately, by doing so, some landmark is under observed, and so the system will be poorly conditioned. Okay? But let me put again the dumping to 1. And the H matrix structure was something that you could paint just by looking at the configuration of the linear system. Interestingly, every landmark is observed by every robot position. Do you see that? And you see it because in this part of the matrix and in this part of the matrix, everything is full. You say, but what is this scattered structure that you see here? Well, this is because of the J omega, the first robot position is not completely full, the Jacobian, right? And so also J omega J will not be completely full for the first pose. While the other poses, maybe they observe much more stuff, and so the pattern will be nicer. Another figure that this program produces is the evolution of the chi-square. So how is going my error? And this is the fall off of the key for the poses, for the key of the landmarks. The key of the projections stays to 0 because we disable the projections, right? Stays to 0. And the number of inliers, well, bumps to high for the poses, and the landmarks, well, they were already considered all inliers. I don't know for what reason. And this is the coolest figure that shows the initial guess. This is the translation part of the positions with the ground truth and the position of the landmarks before and after optimization. Okay. This is the landmarks that end up where they should belong, and this is, I think, the poses that end up where they belong. Okay. Very good. If the visualization is done correctly. Okay, now let's try to do another problem. Let's try to eliminate the landmark measurements and consider a problem where we have a odometry and only projections. Okay? Well, let's see what happens. Nice. What we see, okay, the things go a little bit slower. Before it was like an abrupt fall off, but at the end we observe that our system behaves quite decently. okay? Because the poses end up where they should, and the landmarks end up close to what they should. Why do they end up close? Well, because in order to determine the position of a landmark from a projection, I have to observe it at least a certain number of times. And remember that in our machinery, there were configurations for which a landmark was not observable. You say, but from where do you see that? I see it from here. Remember that the correlation matrix, the H matrix, has some zeros right here. So that here I could easily tell that this landmark over here, so this bunch of landmarks over here, has never been observed, because this part of the matrix which could correlate the landmark with the robot position is 0. And the damping, now you understand why the damping serves to not have a poorly conditioned system. If I would set the damping to 0 and solve this very same problem, I would get a bunch of errors in Octave. Let's try. Boom, boom, boom. Oh, the linear system is bad. And then you see H here. It has these horrible 0 parts that correspond to a 0, but I can't solve this linear system. This has infinite solution. Okay? Yet, Octave does something, because it uses it computes the SVD decomposition, and then it solves the matrix in a rather computational intensive manner, but not nice. Let's put our damping back, run the program, and be happy. Okay, now the last example that it's quite interesting is that what would happen if we would just like run a projection based problem. So we delete the odometry. What would you expect to happen? I'm waiting for answers anxiously. Now I suppress the landmarks, I suppress the odometry, and I'm running just with the camera. Look carefully. The system worked, right? But can you say something if you look at the solution for the landmarks and for the robot poses? You might see that I found a solution, but the solution that I have found, which is the blue one, is a little bit smaller than the other one, because I cannot observe the scale. If I have only camera projections, I cannot observe the scale. And this is an example, it reflects in our implementation, in our problem, by having the word which is a little bit smaller. If I would remove the damping, I wouldn't be able to solve this problem. Okay? And this is consistent with the story, with the fairy tale of total least squares. Now, the message of this whole piece of code, I wanted to provide you with a deep illustration, first of all, to render you aware of a lot of little tools that you have, that we provided you in the course, a lot of little components. And also because the least square machinery has an additive nature, and adding a sensor in the end can be done quite straightforwardly just by putting something more into an existing system without changing whatever it's behind. Okay? Now I need 5 minutes. I need to drink because I've been speaking endlessly. We take 5 minutes break. I will leave the streaming on because I don't know whether today Google is not our friend. Let's see us in 5 minutes, and then I will proceed with another part of lesson. Okay, so 10 minutes break. Let's say 10 for me. Then we continue. Okay, stream will be on. Let's say. I found this. Sounds nice. Okay, we are back, and I think I will not manage to do the exercises, but maybe. Second part of the thing. I recommend the second part of the lesson. But before starting for the second part, I recommend you to play with these totally squares, because it will be the key for many little projects that we will be assigning. Play means change the noise, try to see what happens if you start from a wrong initial guess, introduce a new error function. Maybe you could introduce the function of the polar projection that we have already mentioned. So you can do things with this stuff. And then now, second soup. And now we have a new introduction of this year, is the course map. So we have come at the end of our journey. Now the projects and some exercises, but I think the core part of the course is over, and so I think it's relevant to make a little wrap up of all the things we have seen. Not that much the wrap up from the point of view of the single topics, but a summary of what I would like to leave you at the end of probabilistic robotics. So we started with high hopes, right? This was copied from the introduction. Like I promised you that we would learn filtering tools with discrete Gaussian particles, and we will do a lot of maximum likelihood estimation, which is actually what we have done in the second part of the course. I promised you that we would do data association, and we have done it with greedy heuristics, with voting schemes. We have not done spectral methods, and actually I might introduce something, talk a little bit maybe next time about spectral methods, but it's not that, let's say, it will not change the message of these closing remarks. These were the tools, and this is what I would like you to carry on. In particular, to understand the tools, we have seen many applications on tracking, calibration, tracking, like tracking means projective ICP that you have seen, where you want to track the camera position over time. We have seen localization, you have seen mapping and SLAM. So we have seen a lot of things, right? With concrete examples and with fragments of code that aimed at grounding the concepts, which sometimes are a little bit abstract from theory. So to see the things working. And this was more or less a map of configurations, of facts, of tools, and situations that allow us to use certain tools to model or to the particular reality of to solve a particular problem. So we start from the reality, the world, the environment where our robot, our system has to operate in. We figure out that given that we are lazy, and we don't want to model the things too accurately, we don't want to model the micro distortion of a lens, we don't want to care about the fact that the wheels of our robot change in diameter when the robot is loaded, or maybe there is noise. Well, the deterministic description of the reality that we might give by looking at it does not capture or does not explain the measurements or the phenomena that we observe to its fullest. So we said, you know what, instead of talking about a deterministic system, we could talk about a set of probabilistic rules that correlate a set of random variables that describe potential outcomes of a phenomenon. However, what do we do with the modeling? Everything becomes a floating probabilistic universe, and we don't know then how to interpret or how to what use to make of our efforts that we invested in explaining how a robot moves based on the kinematics, for instance, or how a camera observes the things. Luckily, we could throw in our modeling by defining or observing the structure of a phenomena and seeing that only a few quantities are causally correlated. And we introduced the concept of conditional probability as a way to express basically what was originally a causal effect. Like normally, you define the output of a system or the transition function of a system as a function that deterministically maps input and controls to next input previous state and controls to the next state, and this is a deterministic transition. You could capture that in a probabilistic fashion by talking about the potential distribution of future states given the inputs. The distribution was shape changes based on the inputs that you give in. And if you have a complicated system, you might have many of these deterministic rules that then in the end translate into conditional probabilities. And then we have introduced the concept of manipulation of probability. What does it mean? Marginalization, conditioning, and all these nice things that we have been doing in the first parts of the course. And we have figured out that we can do inference in that. In particular, of all inferences that we were doing on this probabilistic model, when we have a dynamic system, we could write it down in a stochastic form by using a transition model, an observation model, and derive recursive filtering equations. And that holds regardless the way it's used to describe the posterior probability, the belief of my system. And this was our generic derivation of the filter. Then to nail it down in a simplistic form, we derived the first histogram filter with which we made our robot localizing in this grid way. But then we started focusing on parametric representations of the belief. And of all parametric representations, we focused on the most common, the Gaussian. And if you put the filtering implant into the manipulation rules for a Gaussian, you end up with a Kalman filter or if you do the linearization trick, to the extended Kalman filter. And the first thing we were doing with an extended Kalman filter, if I recall correctly, was a 2D localization. Then, happy of that, we extended also the problem with LAM. Actually, we also extended the problem with bearing-only localization, like to show that even if our sensor is poorer in the sense that it's less informative, the filtering can cope with that. Yet this filter for localization required to have a reasonably decent initial guess to then get hooked and capture the belief and track the belief of over the possible robot locations in an adequate manner. After playing with localization, we bloated a little bit the state of the system and we boiled down the 2D SLAM. In doing so, we figured out that the state is something that can change during the evolution of my estimation process. As long as I need new things, I can throw in new things and keep on estimating them. And this was the first version of SLAM that we have ever seen. But at this point, we had still a quite strong assumption that was like that our sensor was capable to identify which measurement was coming from which landmark. And so we started relaxing, given that this is unrealistic, we started relaxing this assumption. This assumption stems from, this is a fact that stems from the fact that in reality, the sensor measurements might look alike regardless from where they are taken. This is called sensor aliasing. And then taking the sensor aliasing and the filtering implant, in particular the posterior distribution, the distribution over the states of our filter, we casted the data association problem. That at the very end we boiled down in 3 simplistic heuristics that allow us to guess an data association to solve this combinatorial problem to the maximum in its maximum likelihood fashion in a conservative manner, and we had our first version of fully functional Kalman filter SLAM that operates without data association. Yes, this special program would require a front end, a driver that takes in raw sensor data and extracts high-level landmarks in the form of points. Curiously, for localization, we didn't have to cope. For this histogram localization, we didn't have to cope much with data association, if you recall it correctly, because we were able to track a distribution that was multimodal, that had multiple maxima. In a histogram, you could do whatever you want. While we needed to do this in SLAM. In the Gaussian case, because then in this case we have a monomodal distribution. After providing these heuristics that work for tracking a data association, they don't invent the data, they don't solve the data association, they assume that you have a reasonably initial guess of your pose, and then they try to shoot potential candidates or the most likely potential candidates. But something can go wrong anyway. If it goes wrong, it goes wrong. After playing with this data association game, then we went back to the filtering implant and we were talking about alternative representation of the Gaussian. A Gaussian can be represented as a set of parameters, but also as a set of deterministically drawn control points that describe the shape of the ellipsoid, basically, of the covariance matrix. And this led us that go under the name of uncentered transform, and then we introduced the uncentered transform and we applied it to 2D localization, but its application to 2D SLAM is straightforward. The benefits of this over this is that the UKF can capture better the nonlinearities and doesn't require the calculation of Jacobians. But it's still a filter. Okay. The final, and we derived the UKF by using the manipulation rules for the Gaussian only in a different form. So all the filters come out from the generic derivation, which was done once, and then by instantiating this derivation to the particular manipulation rules for the type of belief chosen in the instance of the filter. Discrete, histogram, Gaussian. Here we have the parameters, covariance matrix, and mean. Here we have sigma points. Finally, we have seen the particle filter as a result of defining some belief and the operation that on it that work on it. That is a sample distribution, a set of dots, right, in the state space. And with the particle filter, we were once again approaching the classical problems, in this case a 2D localization. Funnily, given that the state space is rather small, the data association wasn't a big issue because for the 2D localization with the particle filter, because we could do a per particle data association. and therefore we didn't have to cope much with this uncertainty. Yet, for doing the data association, so to actually evaluate our particle weights, we had to choose some landmark. So we were doing a per particle data association in that context. Okay? After, what do you take home of this part of the course? Well, what you will need at the exam is this, the methodology. So once you have a filter, but also in your professional life, you need to be able to write it down, to make it functioning. And to make it functioning, this is these are the rules. You start qualifying the spaces with the domain, remember it, and the parameterization. Like, in particular, the state, you have to be aware what the state is and how to represent it, what the controls are and how to represent them, and what the measurements are and how to represent them. After having chosen these, you might start qualifying the transition function that tells you how to move to the next state, and to qualify the measurement function. This is part of the system identification process. In answer to the measurement function, you have to ask yourself, how could I predict my observations assuming that my state is all fine? And after you have done this set of tasks, you might start asking yourself whether you have all you need. One of the things that you need to ask yourself is, are the parameter representation conformant with the operations that the filter do? And the most critical operations are the subtraction of the innovation, basically, where you calculate the difference between prediction and observation, and when you apply the perturbation. And you have to ask yourself, do I need normalizations? Now, something that I didn't tell you, but I will provide you a document, is that there are also formulation of the filtering that operate on a manifold, where basically you decouple the way you represent your mean, the state, which could be whatever you want, the classical state of least squares, from the way you represent the uncertainty. And if you represent the uncertainty of the filter in a chart around the point on the manifold which is described by the mean, which could be, let's say, a rotation matrix, a transform, a point on the sphere, whatever, right? Then you end up to a new formulation of the filter, which is much more robust and which does not require normalizations. Another aspect that you might want to respond while you do the exercise, or while you do the exam, is that, is the state rich enough? Because normally I ask you in an exam, for instance, where you have unsynchronized GPS problem, I ask you just to estimate the position of the robot. But sometimes the position is not sufficient in order to predict the next position, let's say, or to generate the measurements. Because in the unsynchronized GPS, you don't have the time difference. We have seen an exercise on that. You don't have the time difference between your clock and the clock of the satellite system. And so a reasonable thing would be to introduce this element in the state and to carry on this estimate, maybe using an identity as a transition function for the time difference. So the question is, like, is the state rich enough to predict the transition and to compute the measurement? And if not, what should I add? And if I add something, how do I evolve this something? Okay, this is regarding the filter. This closes the first part of the course, and then we have the second part, which is the least squares epoch. Once again, we started from the reality, then due to the noise and poor modeling we can capture with probabilities. And once again, with structure, we come to a certain notion of conditional independence that will allow us to do some inference. If we restrict ourselves to Gaussian noise models, and we are interested in estimating the most likely mean given a set of observations, then we have the Gauss-Newton algorithm that is in the end least squares. And the first problem that we were tackling with that was calibration. You remember the first example was a calibration problem with least squares, where we wanted to calibrate a set of kinematic parameters of the robot. The second problem that we were tackling was point registration, where we didn't yet, but in 3D, where we did not yet have an idea about how complicated the state space could be, and we were doing in the naive Kalman way, that by vectorizing the measurements without really taking too much care about the singularities of this representation. After doing that, we asked ourselves, hey, but where is my covariance matrix? In the end, okay, I'm obtaining an estimate of the potential mean of my system, but what about the uncertainty? And so we figured out that the very least square process gives us for free the error, the information matrix or the covariance matrix, if we do the inversion, of the computed solution. And by looking at this matrix, we can say whether we have enough measurements or whether our problem is well posed. And we might decide to use this covariance matrix or this estimate in order to take some discriminative actions in the remaining part of the system, maybe to stop the robot when the noise is too big, or when the estimate is bad, or maybe to drop some landmarks that are not well observed. For instance, in a point-to-point, in a projective registration problem, if I observe the landmark only once, I do not have any way of defining the z, the distance of this landmark, and I will find this into the H matrix by observing that the block for that landmark is as an infinite uncertainty along the axis of the direction. Okay, then after doing all this soup, we focused on non-Euclidean spaces, and we introduced the box plus as a box minus as a powerful operators to hide the complexity. And while doing so, the least square calculation of the system slightly changed, because we constantly operate on a perturbation along the chart, but we re-evaluate the chart as long as the system evolves during the iteration. So at each new iteration, we calculate new charts on which we solve the local problem. And then we went to point registration in 3D. However, the reality, also in the case of least squares, is subject to sensor aliasing. And so, which means that measurements might look alike. And least squares is a one-shot process in general. And so, you don't even have the benefit of the Kalman filter for integrating the things over time, like that will allow you to implement the heuristics, and you have to find a way on how to solve the data association in case this is not known. And we introduced the voting scheme, RANSAC, Random Sample Consensus, that allow us to reject false measurements and take into consideration the good one based on the consistency of a solution. And this works in case we have absolutely no clue of an initial guess. However, in case we have a reasonable initial guess, in the case of least squares, we found that robustifiers, which is a way of reducing the influence of an error from quadratic to non-quadratic, might be linear, might be clamped, might be inserted into the game. And we have seen an application of a very naive robustifier to the point registration problem at the manifolds. And given that we were moving in the manifolds, we also implemented another program which allow us to determine the relative rotation, translation, and scale about two scenes, and we call this problem similarity registration. Still diving in the registration problems, another stuff that I proposed you was this direction registration approach. I don't even know whether I implemented it or not, which was a generalization of the projective registration system that you have seen in its entirety by Tiziano, and that was incorporating, would say, close to production or close to usable system in reality, where we embedded a different concept of this course. We embedded some data association heuristics calculated from the distance map. We embedded a least square solver, but we embedded the knowledge potentially of an odometry model. Now we didn't put it, but we could. And we boiled down a projective registration system that combines different aspects of the course. We also have learned some techniques. We have figured out that sometimes the problem is too complicated to be solved in one shot, and in case the initial guess is too poor, we might relax some constraints on the initial domain of my problem and recover them later on, hoping that the measurements are fine enough. And we introduced the technique which is called linear relaxation, which consists basically in eliminating some constraints on the domain of the state, ignoring them, and carry on the estimate of the full blown up parameters, while at the end of the solution recovering a minimal form or re-embedding the constraints to these parameters. And we call this technique linear relaxation, and we used it in point registration. Where is the structure? Where is the structure? All the problems that we have observed, we have seen so far, are quite dense. We approached point registration, we approached calibration, where the state space was rather small, was typically the robot position, but one robot position, not many robot positions. What happens in the context of SLAM is that if you want to formulate it in least squares, where the time becomes the space, because you have to consider the entire trajectory of the system, is that the dimension of the problem grows brutally. And the question is, can we use the structure which stems from the conditional independence to do something more efficient? And the answer is yes, with the usage basically of proper methods for storing the coefficient matrix and the coefficient vector. Well, that one is not sparse, and by using solvers that deal with sparse structures. And we introduced today, actually, and last time, a way to describe generic least squares problems in a unique language, which is the language of factor graphs. Factor graph is a machine where a graphical representation where nodes have two colors. Red nodes represent variables, black nodes or blue nodes represent measurements, and I cannot go from a variable to another variable without first passing from a measurement. And a measurement is connected to all the variables that influence the measurement itself. In this context, we have seen multi-point registration at first, then we have seen pose graphs, and we have seen also an example that was comprising everything, which we called total least squares. Now, what do we take of this? Well, once again, we take the methodology, and two methodologies are here. One is the least square methodology, which is not much different from the Kalman one. You start from taking a problem and asking yourself, what is the state? What are the things that I need to estimate? What is their domain? is their domain Euclidean or not? If it's non-Euclidean, how do I parameterize it? And if it's non-Euclidean, how do I define a perturbation? If it's non-Euclidean, how do I define a perturbation for this space that applied to the parameterization of my choice brings me to another point of the manifold? And once I define this operation, which could be also defined programmatically, means a procedure, I could define a box plus operator. We can do the same for the measurement space by qualifying the domain, by defining an Euclidean parameterization for the perturbation, and by defining a box minus operator that returns us the chart difference between a prediction and an observation, or in general between two elements of my measurement space. And in this way I boil down the entire least square system to these 8 steps. Once I have defined my domain, the straightforward thing would be to define the prediction functions, which is, assuming I know all the states, how do I calculate the measurement I should expect given the current state configurations, and then define the error functions if needed by incorporating the box minus into the H. Okay? And the last one is the ransack. In case I give you some exercise on ransack, well, or in case you want to approach a problem in your professional life with ransack, you need to think that ransack is a schema, and in order to cook this recipe, you need some ingredients. The first ingredients is, well, knowing the state, knowing what you want to estimate, but this is, at this point, clear. You need a procedure to seek for correspondences. I mean, is there some invariant in my domain that will allow me to drop constellation of candidates, of correspondences which are absolutely not alike? Imagine that I want to register 3-point clouds, and if I choose the correspondences between 3 points in the reference cloud which are distant 1 meter, and 3 corresponding points in the other cloud that are distant 10 centimeters, well, I already know that this will never work. This will not provide me something reasonable, because the distance is something that is preserved under the transformation. So it would make much more sense for me to select 3 points that whose distance is similar to the distance in the 3 other points in the other pool. And then we need a procedure to compute the solution which is immune to the poor initial guesses, having a minimal number of correspondences. And finally, we need a procedure to count the inliers, because once we have registered the 2 clouds or solve our problem, we need to figure out whether the selection of the initial correspondences was fine, and to do so we need to verify the error for all other points or other elements under the transformation or under the parameters that we have computed with the minimal solver. Okay? And then this is the another cookbook on how to implement or to approach a problem with ransack. After having designed a system sometimes, and this is worth more than for the exam, that it's in the end thing is for your professional life, you might want to ask, okay, I've done this fantastic thing, formalization, it also works, but what are the potential weaknesses? And this can be identified in the things that I've written here, which is the noise. I mean, okay, my system works really well, but as long as the noise is a little bit more than 1 pixel, everything gets destroyed. Is it sensitive to outliers? Like if there is some wrong data association or some point, some sense aliasing, does it break? Or it's immune to that, or it's immune to a certain level of outliers. Is it sensitive to the poor initial guess? So when I start my localization system, do I have really to anchor the robot to the base station and say, now go, or I can just turn it on wherever I want? And also, another thing is like, how does my system operate in underdetermined conditions? Like, might be that you observe the landmarks very seldomly, and then how does it work with this poor observations. Does it degrade, or is it able to recover whenever you see something again? And then once you have defined this, you figured out how good it is in the operating condition, you have also to ask yourself, does it need to be so good? I mean, meaning that sometimes in an industrial system, when you construct the things, you can to eliminate the problem at the root. Like, for instance, you might decide to solve the data association by using as landmarks some QR codes that you stick on the wall. So then in this case, the outliers do not exist, and as well, the data association problem does not exist. Or maybe in case you have a fully automated system, you don't care about the initial guess of your stuff, because you might assume that your robot always starts from the base station, and you know where the base station is, the docking station. But if this is not the case, you might think about possible workarounds, mining in the techniques that we have implemented now. My suggestion is always to start from the simplistic setting, no data association, low noise, and whatsoever, and then add complications later on, rather than thinking about a super complicated system that deals with everything from the very beginning. And sometimes we all start from an idea, we have something that works, but it doesn't perform as we want it to perform, and it's not usable. And in this case, my highest recommendation is like not to be proud, to throw it away and to redo something from scratch based on different ideas. Maybe you started a problem thinking the filtering was the best solution, and then you figure out that filtering is not enough and you have to go to least squares. Now, and that's, well, just be flexible, take it as doesn't work, let's do it again. And in doing so, my recommendation from the operational point of view is always to try to go vertical and to make your system failing as soon as possible. Because if it doesn't fail when you want it to fail, then you're on a good track. And I think I conclude this last part of the course with some recommendations on when you have to operate in these systems. The first one is visualize the data. Now, once you're given a data set or a problem, before even you start coding, you have to build or to write a viewer, not a program that writes things on the screen, some display of the data, so that you visually realize what's going on. And also it provides to be a very useful instrument for debugging later on. First one. Then if you have an estimation problem and you understood the model, then start to construct a simulator that generates synthetic data, and then compare this synthetic data with the data that come from your data set to see if you understood correctly that the system works as you have in mind, right? This is recommendations for your professional life, not for the exam. Once you have that, you have a simulator, and you have a system like all the programs that we were constructing in Octave started from mocking a word and simulating some sensors. You have a program that allows you to have a ground truth estimate, which is unpayable, because you know when the things are wrong, and you can debug exactly the portions where there is a difference between what you expect it to be and when it's not. It's very common that we blame to the noise everything, but rarely the noise is the cause. Normally it's some mistake we did before. Once you have done that, you can write down your error functions, but your error function you have already written because you did the simulator before. You wrote the predictions, but the error functions are simple at this point. And you have to be sure that if you start from the perfect configurations, the system error, the difference between the prediction and the observation, is 0. Similarly, you have to be sure that the open loop transition model, in case of a filtering problem, returns exactly or follows accurately the ground truth if there is no noise in the controls, no noise in the state, and no noise in the bus. Another, once you have done that, you're left with the last portion, which is the construction, the calculation of the Jacobians. But on average, in a real problem, you normally first you calculate them numerically, locally at the beginning, and then later on, if you see that there is a performance issue, then you go on and you write them analytically. So this is not a course on Jacobians. Another recommendation is don't write all on paper and implement it all at once, on the one hand. But the other recommendation is the other way around. Don't implement everything and figure out that it doesn't work and go back to the paper. You have to do both. A little bit of paper writing, understanding, okay, let me test it. Paper writing, understanding, let me test it. Okay? This is more or less a modus operandi of this class of problems and of systems. But I think a lot of these suggestions might be applied also in different scenarios. Now, if you have questions, please write them in the chat. We did not make it to the exercises, but if you have questions, I'm here to answer. Okay? And while you write the questions, because there is a latency, let me say one thing. It has been a torture doing this course without seeing you in the face even once. I was struggling a lot because while I was talking, I was thinking about the potential questions you might ask, because you don't ask questions, right? So I was thinking about the potential questions you might ask, because I have never seen you even once. And normally when you are in the classroom, you can go much faster and stop upon demand. And doing remote lessons requires, it's more effortful because you don't have a touch with you folks, and you're not very proactive in writing and asking things, but you won't be ever judged because of that. There's no stupid question, or this only stupid question is this question which is not asked. And well, I'm waiting for questions, or otherwise I send you to have a nice lunch. In the next lesson, we will see, while you maybe think about something, we will see project assignment, and we will talk a little bit about the exam, and we will do an exam sample. And also in the, I don't know if I'm allowed to give lesson on the 22, please answer at least to that. Also on the 22 we will be doing another exam sample, if they allow me to do lesson. No questions? All right. Well, then have fun, enjoy. See you on Friday. Oh. Ciao, ciao.